Okay, this is a question where you're asked to do to work out an empirical formula from combustion analysis. So you're told you've got an organic compound, you're told it's made of carbon, hydrogen and oxygen, and so you know the formula is something like CnH, I don't know, letter P we can call it, and O X. Doesn't matter what letters you use. It's some sort of relationship between carbon, hydrogen and oxygen. You're told that when you burn this stuff, which is called carbone, it produces water and carbon dioxide. I think you know that when you burn organic compounds, you react them essentially with oxygen, right? And you're told in the question you're reacting it to give carbon dioxide and water, okay? So when thinking about these, I always write out the equation kind of like that in full. And however many moles of carbon there are in the reactant, there must be that many moles of carbon dioxide, okay? Because carbon dioxide's got one carbon in it, and the only place that carbons can come from is the carbone. The number of moles of water, though, will be half that of the number of moles of hydrogen in the reactant, because there are 2 hydrogens per water molecule, so it's P over 2 waters produced. I find that useful to think about, even if we don't necessarily use it. So what you would do if you're unsure what to do in any calculation is to work out the number of moles of stuff. And I'm not going to write everything underneath in such detail just for space reasons. But the only information I've got at the moment is that carbone is 0.2136 grams. Water is 0.1793 grams. And carbon dioxide is 0.6254 grams. So let's at least start by working out the number of moles of things that we can work out the moles of. And you can work that out by using the formula masses. So this is what I'm going to do. I'm going to set it out slightly differently from the grid here because there's lots to get in. So the number of moles of carbon dioxide is equal to the mass divided by the formula mass, which is 44 whatever it is. I'm just going to use whole numbers to make it easy for me. And that comes to 0.014, can't read my own writing, 18 or something like that maybe, depending on how many decimal places you've used for that, but it's been more or less that number there. The number of moles of water is equal to 0.1793 divided by 18. It would be 18.02 for water. We'll just do it to a whole number. That comes to more or less 0.010. There's maybe a few decimal places after that, moles. Okay, that's how many moles of water there are. Now, we're trying to work out the empirical formula, in other words, the molar ratio of carbon atoms, hydrogen atoms and oxygen atoms in carbone. So we need to work out the number of moles of carbon and the number of moles of hydrogen. The number of moles of carbon is equal to the number of moles of carbon dioxide, right? Because each carbon dioxide's got 1 carbon atom in it, so that's just the same number. The number of moles of hydrogen, though, is not the same as the number of moles of water, because each water molecule has got 2 hydrogen atoms in it. So there must be twice as many moles of hydrogen atoms as there are molecules of water. So 2 times 0.01 equals 0.02 moles. Right? So far so good. I'm getting but we then have to work out the number of moles of oxygen that were in the carbone. We were told the mass of the carbone, but at that stage we didn't know how much of it was oxygen. Now if we know the mass of the carbon and the mass of the hydrogen in carbone, we can work out what the mass of the oxygen in carbone would have been. We can work that out if we know the mass of the carbon and the mass of the hydrogen, which we can get from the moles. 0.0418 moles of carbon times by 12 is the mass of carbon, right, in grams. And the mass of hydrogen is 0.0 times by 1, because hydrogen's got a formula mass of 1, so we can do that one. The mass of carbon I got to be 0.1706, and again the numbers might vary a bit depending on how many decimal places you've used. So that many grams of carbon are in there, that many grams of hydrogen were in there. So we can work out, can't we, then, the mass of the oxygen in our carbone by doing the total mass of carbone, take away those two numbers. And when I did that, I got that. And so I can work out then the number of moles of oxygen. Moles equal to mass divided by the mass, the atomic mass of oxygen. So not that divided by 16, and I got that to be so now I'm in a place to work out the empirical formula, which is just the molar ratio of the elements in the compound. So if I set it out the way that I would have taught you at the time, so carbon, hydrogen and oxygen, if we write down that, I'll spread it out a little bit for space, carbon, hydrogen and oxygen, the number of moles of each one, I'm just reiterating now what I've already told you, 0.01418, 0.02, 0.00144 or thereabouts, okay? Now they're not whole number ratios, so that's not very useful. To turn these into whole number ratios, we divide them by the smallest one of these numbers. This is the smallest one of these numbers, so we do all of these numbers divided by that number. The molar ratio we get, that must be 1, that divided by itself is 1. That divided by that, I got to be, well, I can't remember writing, is it 14 or 19? 14 I think. And that number divided by that works out to be more or less 10. So the molar ratio is C10, or the molar ratio of elements in the compound is C10H14O, and that is indeed the empirical formula and the molecular formula of carbone, as it turns out. Okay, that's that. Lovely.